Okay, our next topic area of study is sequences and series. These are number patterns, so we're starting off with sequences first of all. The set of sequences is a number pattern. So a number pattern. And there's a few different ways that we can write them down and describe them, probably should say. The first way we can describe is by listing in order. Okay, so that's the first one. So a sequence may be something simple as 3, 5, 7, 9, etc. It's a fairly simple sequence. Could be a little bit more complicated than that. Say 1, 1, 2, 3, 5, 8, and so on. And another example of a sequence might be 7, 11, 16, 22, 29, and so on. So each of those, again, is just a list of numbers listed out in order, and there is some sort of pattern that happens in between each of those so that we can actually describe those. Okay, so there would be words also, of course. Okay, so the next way that we can write or describe sequences is what we call a functional definition. And functional definition is we express each term in the sequence in relation to the term number. Okay, so if it's the fourth term, there's some sort of relationship between what its value is and the number 4, the fourth term. So something that we might do would be something like this. So term n in this particular sequence, say maybe something simple like 2n minus 7. And n in these cases is an element of 1, 2, 3, 4, and so on. Like that. So then you would just simply, if you want term number 1, you substitute 1 into that. 2 minus 7 minus 5. The second term, term 2, substituting 2 into that. 2 2s are 4, take 7's minus 3. Term 3 is minus 1, and so on for each of those terms. So that's a fairly simple one. We can of course have functions that will be more complicated than that. So say, for example, this one here is Cn, term n, say is cos n pi plus 1, where n is an element of 1, 2, 3, and so on. Now, this one's quite an interesting one, in that your sequence, if we listed it, ends up being 0, 2, 0, 2, and so on. So, that's quite an interesting one, but it's still, even though it doesn't seem to be much of a pattern, there is a pattern there, and we can describe it. Okay, so that is the second way. The third way that we can describe them is what's called an iterative. iterative definition. So each term is described in relation to the term before. Okay, so something like this, for example, term n plus 1 is, say, 3 times term n minus 2. Now, here we need to know, though, if we're after, say, the second term, we need to know what the first term was, and that sort of thing. So for these iterative definition, you need to be given a starting point. So say this one here, term 1 is equal to 6. So if term 1 equals 6, this one would go 6 to start off with, then you got 3 times 6, take 2, 18, take 2. Then you got 3 times 16, take 2, 46, and so on. However, if we started with a different starting number, say the number 2, then we would get a different series here, because 2 would be first one, 3 2s are 6, take 2 is 4, 3 4s are 12, take 2 is 10, and so on. So this iterative definition can actually give us different sequences. So that's why we need to know what the starting point is. Okay. Okay, so we're back looking at our calculator. So our calculator can be used for it. So to work out these explicit is, sorry, you need to get to where you find the calculator. So from your main, or from the menu, you scroll down, one of them is called sequence, that's the one we use. And then you'll notice there's 2 tabs on them. One has explicit and one has recursive. Now, explicit relates to our functional, and our recursive relates to our iterative. Okay, I'll give you a hand with that when I come around. You can also have a look at pages 181 and 182. There's examples there on those. How to use that. Alright, last thing is what's known as a thing called the logistic equation. And what the logistic equation does is it predicts population next year based on this year. Alright, so what it looks like is this. So it's something that statisticians and that have come up with, and they've said that the population next year is some constant times the population this year, 1 minus the population this year. A is a constant, and 0 is less than 2, 0 less than 1. Okay, is the restrictions on it. So let's look at an example. So given A equals 2 and T naught is 0.7, generate the first 6 terms. Of the sequence using the logistics equation. Alright, so there we go. So that's that. So if we go here, let's start at the top, because what we have this time is that term n plus 1 equals constants A, so 2 term n, 1 minus term n. Okay, so term 1 then equals 2 times term 0, 1 minus term 0. That of course is 2 times 0.7, 1 minus 0.7, and when we do that we get 0.42. Term 2 then would be 2 times 0.42, 1 minus 0.42, which would be 0.4872. Term 3 is 2 times that, times 1 minus 0.4872, and when you work that out you get 0.499673, and so term 4 comes out to be 2 times that, 4996723, 1 minus 0.499673, and when you work that out it comes to 0.4 and a whole bunch of 9s here now, 3, 4 or 5 of them, and an 8 on the end. So term 5 is 2 times that number, getting lazy here, 1 minus that number, and when you do that you get 0.5. So term 6, 2 times 0.5, 1 minus 0.5, and that's 0.5. Okay, so now this sequence here, you'll notice about that it finally gets to an answer of 0.5. So what we would say about this is that it's convergent. So it converges on a number, and the limit is 0.5. Okay, so you could use a calculator in the recursive to do that as well. Alright, so that's it. So question set number 1, exercise 6A.